Hello, welcome to the 15th TAISIG Talks. These are the last TAISIG Talks of this academic year. Though not the last TAISIG Talks overall, because we will continue with this next year. In this 15th TAISIG Talk, we will have a program with two people, Murat Kirtay and Giacomo Spigler, who are both interested in robotics, but from a different perspective. My name is Peter Spronk, my co-host is Marie Postma, and Marie will now introduce the first of our two speakers.
Thank you, Peter. Good afternoon. Our first speaker is Murat Kirtay. Murat is assistant professor in the Department of Cognitive Science and Artificial Intelligence at Tilburg University, where he is focusing on autonomous agents, gaming, and robotics. He has a background in computer science, and before joining the department quite recently, he was a postdoctoral researcher at the Humboldt University in Berlin. During his PhD at Scuola Superiore Sant'Anna in Italy, Murat was a part of the Human Brain Project, where he contributed to the development of the neurorobotics platform. His research concerns modeling human condition and intelligent social interaction in humanoid robots. What's interesting about the interaction is that it can be human-robot interaction, but also robot-robot interaction. For example, in a situation where two robots are interacting, one of them being a caregiver and the other one being an infant robot. In his work, Murat is creating properties for robots that we tend to think of being typically human-like properties. So among other things, he proposed to model emotions in artificial agents by means of computational cost of perceptual processing in a decision-making agent or a decision-making system. And the same mechanism can be used to simulate trust of a robot towards its interaction partner. We're looking forward to your talk, Murat.
So today I will talk about humanoid robots for symbiotic societies. Basically, I'm using this umbrella term to introduce my postdoctoral research. And in particular, I will defend or advocate the interdisciplinary research in this direction. So to conduct research in this direction, first I need to set my goals. And here is three steps of my goals. First, I am collaborating with psychologists and neuroscientists to extract core components of intelligent social interactions inspired from cognitive developmental systems and validate these models by using either physically or virtually embodied agents. Oftentimes they are humanoid robots. By achieving first two goals, my last goals is to contribute to future of symbiotic societies by making these robots more trustworthy for their interactions in society. So now we set our goals, but we need a research framework to achieve these goals. And this research framework comes from Cluster of Excellence in Berlin. Here we had a framework to collaborate with people from different disciplines. And this framework called analytic and synthetic loops. In this, to achieve this framework, first you have to define your goal as a team, as an interdisciplinary research team. And the goal is intelligent social behavior on humanoid robots. And this framework will enable to integrate knowledge between two different disciplines. The analytic side, we have psychology, neuroscience, philosophy, and that kind of disciplines. From the synthetic side, we have more technical fields like robotics, engineering, and other kind of engineering disciplines. And not that this is not a theoretical or a conceptual framework. You are literally, as a roboticist, sitting next to neuroscientists or psychologists to achieve this goal. And let's see what we achieved so far within this framework. And today I will bombard you a lot of different types of research. So if you have questions in Q&A session, we can go in detail. And the introduction of this research project will be quite superficial due to the time limit. So the first project is assessing that whether humans are co-representing robots as a human or in a different way. Okay. From psychology literature, we know that if you are naming an entity or object within the same category, for each object, you become slower. Okay. Like, let's say I am defining my favorite game developers, starting from John Carmack, then Jonathan Blow. And with each name, I become slower. And if I partner up with someone as a human, if he or she named her favorite game developers, I will show the same effect. I'll become slower. So this shows that we are somehow co-representing our partner's speech. Then we integrate a humanoid robot in the setting to assess that, okay, for the humans, yeah, this effect exists, but what about the robots? And surprisingly, we found that this effect does not imply for the robots. Quite surprising fact. The robots, if you partner up with robots, you become faster instead of become slower. And in another research, we go one step further and assess that what is the neural representation of the different interaction partners as a human, as a humanoid robot, and as a computer tower. So we create a simple game experiment. The participant in the scanner interact with these three partners, and we record fMRI data from the participants, and we assess that theory of mind network is activated for all of the agents, all of the interactive partners, but there is a ranking between them. Humans are more, for the humans, it's more activated. Robots ranked as a second, and computer tower ranked as a last one. So these are the most interdisciplinary research that we conduct. Of course, we are also doing some pure robotic research. And you see on the bottom left, in this setting, we are enabling or creating a framework for our robots to achieve a heterogeneous interaction. By heterogeneous interaction, I mean the interaction partners has a different physicality and different cognitive levels. Okay? Like one of the arm of the robot can be short, or robot can generate different sounds. That's the physicality. And this robots also can have a different type of expertise. Like one can be capable of using correct names for a specific category. The other cannot. And of course, we have a framework. We cannot blindly implement this framework onto robots and enable it to enjoy the freedom to live in our society. We need some guidelines, and we are in the process of creating a trust framework based on European and Japanese ethics standards to make our robots more trustworthy. And later I will go in more detail. We also have another ongoing projects, starting from robot-robot scaffolding and designing a teacher robot by using the human teachers' gestures and realizing them on robots and employing them on classroom. And on the bottom left, you are seeing one of the latest works. We are using a gated multimodal reinforcement learning in here. Here, the Now robot interact with three different partners. Each partner has a different skills, and Now robot is differentiating skills of its partner. And tonight is a submission date of this paper, so wish me luck. I think cross your fingers. The last project in here is on the discussion level. We are planning to provide a robot as robot self based on infant literature. So in the infant literature, it is quite developmental stage of the infant for acquiring a self is staged. Like in the first stage, it has an ecological self. It cannot differentiate the action of others and action of itself. Everything confined in a single entity. In the interpersonal self, it can differentiate its own her own action and others' actions. At the last level, cognitive self, it can individuate the partners. And this is still in the discussion level, and we are planning to provide a computational model of robot self in this sense. Okay. So up to now, I just abstractly mentioned about what we are doing, and I select a few examples to be more concrete for your questions. Here, what we are trying to do, enable our robots to interact heterogeneous partner as a human and as a robot. Okay, and heterogeneity is everywhere in the world. Okay, in this picture, this caricature you see in here, no two agents are same as a robot or as a human. Okay? So we shouldn't expect our robot will interact with the same partner or similar partner during their lifetime. So to do this, we design a four-layered cognitive framework, a four-layer trust framework guided by ethics principle from European and Japanese one. But today I will not discuss about the ethical principles, just give a computational idea behind this framework. So for the cognitive level, we currently implement three different subcomponents, and I will introduce them in the next slides. So we first create an interaction framework, and this framework requires three different parts. In the first part, you have an agent. Agent should interact with the environment and the interaction partners by using its cognitive modules. And we have an environment. Environment is providing a task to our agent. And task in here is to find a room or patterns which is less noisy for our robot to process. And during the interactive experiment, robot interact with three different partners with different physicality, as a simulated agent, as a robotic agent, as a human agent, and with different guiding strategies, like reliable partner, unreliable partner, and random partner. Reliable one, whenever robot asks help, it will show a pattern, or it will show a pattern that is associated with less cognitive load, less cost, or less energy. And at the end, robot will learn through interaction. It is a simple model-free learning method, and it will distinguish both interaction partners, guiding strategy, and find the patterns that are associated with less amount of cost. Of course, you can say that, okay, this is quite boring grid words, but in robotic case, it's not that simple. It's still, for a single partner, you need to interact with it for more than 20 hours. So it's quite expensive in that sense, time. You can adopt this framework in a game setting, like a Donkey Kong in here. Instead of finding a pattern in the maze, your agent can locate the ladders that are useful to reach and save the sprite or increase the scores. You can also use tabletop games with the actual human partner and robot partner in this setting. But again, it will require a lot of time to play with this game, and human will get bored. Okay. So from the technical side, we have three different components, as I said, but you can add additional component like explainability as a component in this framework. And the first component is a multimodal auto-associative memory. Here we have an energy-based model. It's called Hopfield neural network, but you can use another one like a deep leaf network. And with that energy-based model, you will have an input image, and network will converge into some state. And the operations that reach that steady state we count as an energy or cost. Then we use this cost to feed in our reward function. Basically, if you are moving from high cost state to the low cost state, you make a right choice, and we are rewarding you with +1. You don't need to use -1 or +1. You can directly put the energy to the system also. It will work. And lastly, we have a partner preference formation module, which is a module that provides your agents like Torif-bind-like functionality. With this module, the robot can infer what kind of strategy that your interaction partner is following, and try to avoid that interaction partner during the experiment. And with this setting, basically what you can achieve integrate multimodal information. You can achieve heterogeneous interaction, and you can basically solve this kind of simple maze or game-like problems with your robots. Of course, I introduced a lot of projects in here, and none of them is a solo project. I am working with amazing colleagues, collaborating with amazing colleagues. And I hope in my next talk, I can add people from the Tilburg also. And lastly, I would like to advertise a workshop that we are organizing in incoming IROS. If you think your research is overlapping with one of the topics in here, please let me know, and I will encourage you to do a short paper submission to our workshop. Yeah, that's it from my talk, and I'm ready for your questions.
Thank you. What I didn't get is, what is a high cognitive load for a robot?
Okay, high cognitive load, a sample that it didn't see during its training, and it's contaminated with environment noise, or you are merging with the patterns, basically. If a robot see unfamiliar pattern, it will retrieve a high cognitive load for its perception process.
Okay.
Can I have a follow-up question?
Sure.
So I think this definition of trust is very powerful. So it's basically, it means that you can trust someone's perceptual analysis of the environment, and you don't have to spend your own resources on analyzing it.
Exactly.
Were there cases or situations where you thought that you ran against limitations for this type of definition for robots?
Yes, the limitation is, one of the limitations is the adding additional sensory modality. Like we used audio-visual information, but practically you can also add the motor command of the robot, but that will bring additional computation for our experiment, and we didn't do it. Another problem is noise, both from the robot and from the environment. That's another problem. And lastly, sometimes interacting with human partner forget its script, and it didn't interact the robot with it properly, and that can be some of the problems with our framework.
But you did not run into cases where you thought that you would actually need an additional definition, or that this one was maybe too weak. It was more about fine-tuning certain scenarios, if I understand correctly.
Yeah, exactly. Yeah, that's the one of the things that we should unify within this workshop. Okay, what we mean by the robot trust. Currently, we are just using inputs from psychology to define our trust. But later, I hope in this workshop, we will come more unified definition of the trust.
I have seen some of this research that other people did, where one thing that I found really interesting is that you say, well, people can play games with robots, and robots can learn from that, etc., etc. Where actually the challenge for them was to make the interaction feel natural to the people, that they find it an entertaining game player. So to what extent fits that in your research, and can you say something about it?
Yeah, that's quite interesting question, because we have some meta-analysis studies in the literature, how to make the task more playful, like some anthropomorphic features of your partner, or partner that understand that your cognitive load and act accordingly, like the partner that puts you in the flow. Okay, task will not be, your assigned task will not be too hard for your skills, that you will understand that you cannot go beyond this, and you will disengage with the task. And task should be so simple for you that you can achieve. So your partner should make you in the flow, actually. That's what we. Yeah,
well, these are two aspects, of course. One is the technical aspect from how are you an interesting game opponent or game player, and the other one, so within the confines of the game itself, the game rules and the game logic. But the other is, are you an interesting social game partner, in the sense that is it just the mechanics of the game playing, or is there also that social component? And I think that is more core to your research, and probably the more interesting part of it.
Sure, yeah, the social component is important because, let's say, joint attention. If you are playing a game and you're not paying attention together with your peers, it means that you are not engaged with the task, and that will signal your partner that, okay, this game is not important for me. I don't want to play in that sense. I'm just playing for the sake of killing my time. So there's no gameful component in there.